We are back to integration, and we know the basics of integration. We've gone through it in previous lessons, which I'm pretty sure have even been uploaded to YouTube, and they are on the website, which you can access through there. So we do know how to calculate area through definite integrals, but there are some questions when it comes to like when there's multiple different like functions and you find the area between those, and sometimes dealing with signed area when it goes underneath. But yeah, but essentially we know that if we want to find an area under the curve, we do the definite integral between the two x values in which we want to find that area for. So let's say we want to find this area, we just integrate that function of x from, let's say, 0 to x equals 4. So we integrate from here to there, and you'd get like x squared onto, then you'd integrate that from 4 to 0, you sub in 4, sub in 0, you sub in 4, you get 16 onto which equals 8. And you get an area of 8 units squared. And yeah, that's like the most basic example of finding area under a curve when it comes to integration. But sometimes you get asked relatively trickier questions. You get like a pool, for example, or like a pipeline, and you need to optimize for a specific area. Like they give you the cross-sectional area, that's what they call it. There's that terminology of cross-sectional area to actually understand what cross-sectional area is. Hopefully, I think there's a question like that here today. And if there isn't, I'll be sure to go find one. Another cool thing that we've added, which I'll go ahead and show you guys, is if you do head over to the website. So back to resources, you can find the worksheet that we're going to be going through today. But another thing that we added is this got a tricky question thing where you can actually submit a question that we might see. Yeah, but that's basically it. So resources, you can go, and also if you need to, you can actually go head over to the calendar and you can download it as an IC, so it'll go straight to your Apple Calendar. And also, if you're not in already, do join the WhatsApp groups because we have live updates there as well for session timings. Let's move on to just some area questions. So this is the first question. It's not too difficult. It is just finding the area bound between a region of 3x squared plus 2. So we can draw this function pretty easily. It's pretty simple quadratic. We know it's plus 2, so it will be up 2, and there's no horizontal dilation. There's vertical dilation of plus 2. Sorry, translation. And it's dilated by a factor of 3, so it's a small, tight parabola like that, something like this. And yeah, it looks something like this. And we want to know the area bound by the curve and the lines x equals 0 and x equals 2. Okay, so x equals 0 will just be the x-axis. Sorry, the y-axis, and then x equals 2 will be right here. And so we want to find this area bound under here. And to find that area, we'll just simply integrate 3x squared plus 2 from 0 to 2. To integrate 3x squared, we actually know that the derivative of x cubed is 3x squared, so we can do that straight away just by like identifying it. Or another way we could go about this is the typical power rule of integration, where you add 1 to the area and divide by that number. So if you have x to the power of n, the integral of that is going to be x to the n plus 1, all divided by n plus 1, and of course plus c. But since it's bound, we don't have to worry about that plus c. Okay, so we know that we're going to get x cubed, and then we're going to add 2x to that. We need to bind this to 2 and 0. What's up in 2? You get 8 plus 4. And then we take away when we sub in 0, which is just going to be 0. That will give you 12 units squared as your final answer for that area. So I'll give you guys a moment here, and then I'll go through it. We're going to find the points where it meets the x-axis, in other words, the solution to the equation. So what you could do is, of course, sub in for y equals 0. So sub in y equals 0 to the function is given to you. So we get 0 equals 8 minus 2x squared. Now people go ahead and try to like factorize this, but you can just move stuff around. So you get negative. So then when you move this 8 to the other side, you get negative 8 minus 2x squared, just by like simple algebra. Divide everything by negative 2. 4 equals x squared, and then x equals cube root of 4 plus minus, you get plus minus 2 as your roots for x. And the diagram that they've provided us actually does show that, but you of course need to show that working out. And since it asks for coordinate notation, you get this as your actual coordinates. Now they want us to find the exact area of this region as well. So now that they've asked us to find out the x values, that's where the bounds will kick in, and we solve for the range of negative 2 to 2. for the function. Integrate that, we get 8x minus 2x cubed on 3, again using the same power rule. And this time we sub in 2 and negative 2. Now, since we know it's a parabola, one cheeky way to go ahead and do this, or a trick to do it a non-conventional way, this is to it the integral from 0 to 2, so this half, and then it's multiplied by 2 because you know it's symmetrical, and that way you don't have to deal with negative numbers if you're not a fan of negative numbers. And that's probably what I would have done. So you get 16 minus 2 times 8, and all that divided by 3. And then this whole thing minus 0, since we have that. And that's going to be 16 minus 16 on 3. You get 32 on 3. And of course, we need to multiply this whole thing by 2 because of us removing the lower bound. And instead cutting it halfway, we can only do this because we know it's symmetrical. Of course, this won't work for every function, but it does make it easier on our end. And if you did want to verify that with any other solutions or any other, the regular way to do it, it would give the same answer. So you end up with an answer of 64 all on 3. Consider the curve x cubed minus 4x. A blank grid below is provided to sketch the curve. We don't really care too much about sketching the curve. Instead, they've asked us to show that the curve crosses the x-axis at x minus 2, x equals 0, and x equals 2. So instead, let's just find the roots of the curve. So we got y equals x cubed minus 4x. To find the roots, we just let that whole thing equal 0, just like we did before. Take an x out, and you get x squared minus 4 equals 0. And now you know that this x can equal 0. So x equals 0 is going to be a root. And the other root is going to be, well, this is now null factor law. It's going to be when x squared minus 4 is equal to 0. And you can do the same thing again like this. This is difference of two squares, or as known as dots. X minus 2 and x plus 2. And once again, using null factor law, x equals plus minus 2. Here, so here's our three solutions for x. And hence, since those are three solutions, those are the cross points on the x-axis. And since it's a positive cubic function, we have it going in this direction. So it looks something like that. We don't need to know the exact turning points. They didn't ask us for it. And the graph looks like that. Find the exact physical area enclosed between the curve and the x-axis from negative 2 to 2. In your response, explain why evaluating from negative 2 to 2 of the function does not give this area. So the reason why it doesn't give us that area is, as we discussed at the very, very beginning, is this little negative, this area under the x-axis will count as a negative area, which is not actually, true in the real world. You don't have a negative area. So instead, what we would do is we'd actually get the absolute value of whatever value you get when you integrate from 0 to 2, since we know that's the part that's under the curve. So first of all, what we can do is we can integrate for the part that's easier, part that's always above the x-axis, which is negative 2 to 0, for the function of x cubed minus 4x, x 4 divided by 4 minus 2x squared. Plug in the values of 0 and negative 2. We end up getting, you sub in 0, you end up getting nothing. So you get 0 minus the entirety of negative 2 to the power of 4, which is just going to be 16 on 4 minus 2 and then times 2 squared, which is going to be 4. They're going to get 4 units squared. Now we're going to find the other area, which is going to be the integral from 0 to 2. We're going to get the absolute value of this, of the same function. So yep, integrating it's going to be the exact same. So you end up with that. And the bounds this time are 0 and 2. Sub in 2, you get the same values of 16 and 4 minus 8. And this whole thing is, of course, absolute value. You end up getting negative 4, absolute value of negative 4. It's going to be equal to 4. So now you end up with 4 units plus 4 units squared, and you end up getting 8 units squared. Side note, the reason this works is because of a integration law that they probably did teach you at the beginning. We'll revise it in case you haven't heard of it. It's essentially just the integral from a to b. Let's do this. A to b is the same of f of x is the same as the integral of a, sorry, let's do a to c. A to b plus the integral of b to c of f of x, given that a is less than or equal to b, which is less than or equal to c. So that's kind of what we did there. So in this question, we wanted to find the integral from negative 2 to 2. And we did negative 2 as a, and then for b, we did the value of 0, which was the intersection point with the x-axis when it turned to the negative. And for this part, we had 0 to 2. So yeah, that's how you apply this law in a real world question for like when they ask you to find the physical area when there's a negative component to the question. Here's something more like a CF question. Yeah, where they actually give you a more real-world example. We're talking about a drainage channel with a uniform cross-section, a cross-sectional area. So if you imagine looking at a pipe from above would just look like a rectangle, but if you look at a pipe from the side, you get a circle, and that's actually the cross-sectional area. They've asked to find the x-coordinates of the point where the parabola meets the line y equals 4. The parabola is just y equals x squared, then they're really easy. You have 4 equals x squared, and you get x equals plus minus 2. Cool, easy enough. Those are the x coordinates. Well, for b, you want to find the exact cross-sectional area of this channel. So we're going to find the cross-sectional area now that we've calculated the bounds. We have -2 and 2. And this time around, we're kind of dealing with two functions here. If we integrate from -2 to 2 for the parabola, what we'll end up getting is this area over here. As said, if you integrate from -2 to 2 for the parabola, you end up getting this red area here. And if you integrate for the straight line of y equals 4, you end up getting this entire area in green here. So you'll notice that the overlap between the integrations is this area here. The area that we want is just this green area that's left here. So if you were to take away the integral of the parabola from the integral of the line, you would be given the drainage channels cross-section, which is the same as finding the difference. Finding the area between two curves. You get the upper function minus the lower function. So in this case, our upper function is just y equals 4. So we end up going 4 minus the lower function, which is x squared. And integrating for this should give us our answer. So let's go ahead and just integrate here. Integral of 4 is going to be 4x. Integral of negative x squared is going to be negative x cubed on 3. And now we just sub in the bounds of -2 and 2. Sub in 2, you end up getting 8 minus 8 on 3. And now we sub in -2, we get up and getting negative minus 8 minus, once again, minus 8 on 3. Let's convert the 8 to 24 on 3 minus 8 on 3 minus -24 on 3 plus 8 on 3 is what we have here. And then we're going to end up getting 32 on 3 units squared as our answer. So we'll move on to the last part, which is the channel is 300 centimeters long, hence find the volume of water it holds when full in liters. They've told us that it's actually in centimeters, so that means the cross-sectional area is actually not units squared, it is centimeters squared. We know the formula for volume is the same as area times length. For something that's like a prism, that's what it is. We know that the cross-sectional area is 32 on 3. If we have a length of 300, we know that the volume is going to be 3,200 centimeters cubed. So you get 3.2 liters, since that's the conversion rate for 1 liter is equal to 1,000 centimeters cubed. All right, moving on to section D, question 5. So these are moving on to the more CU type questions. We want to show that the volume of the water that's drained in the first 9 minutes is 216 liters. So when they give you the rate of change, that's the same as dl on dt. If you want to find the actual volume, so that would be L, you can integrate it to find that. So you can integrate from 0 to 9 or 12 square root of t. Square root of t is the same as t to the power of half dt. If you integrate this, you should get your answer. So we have 12 t to the 3 on 2 divided by 3 on 2. And we would sub in our bounds of 9 and 0. 24 on 3 times 3 to the power of 6, square root of that, and square root is the same as to the power of half. And we get 24 on 3 times, now we can use what's called index rules. We get 3, then you get 24 times 3 to the power of 3 is 27 on 3. And you get 216 as your answer. And looking back, that is what they wanted us to show. So we know we're probably correct. Okay, a bit easier than I thought it'd be. It's just 500 times 216. So we really don't even need to do any math there. All right, we'll just move on to part C. Without further calculation, state whether the water is draining faster at t equals 1 or t equals 4. Justify your answer by referring to RT. At t equals 4, it'd be draining at twice the rate of t equals 1. And the values do without for the calculation, but I don't know how else you'd explain it without it, because RT is a square relation. So at t equals 4, that's going to be 2 times more than t equals 1, because at t equals 1, the rate is 12, and t equals 4, the rate is going to be 24 liters per minute. Liters per minute. But yeah, it's faster at t equals 4. And I'll give you guys a moment to actually go ahead and do this. When you find these type of questions with the variables, that's when we get into the CU type of territory, where we're trying to find the region bound between y equals square root of x, so square root of x is kind of like that, and the line a x equals a. So I think always for these type of questions, it's always great to draw a graph, especially if you can, because I'm sure most of us by now know what square root of x looks like as a function. And we're going to find the line a, so the value of this a, such that the area under this curve is 18. So another way of phrasing this is from 0 to a of the function square root x dx is going to equal 18. Now, this is just one simple calculator sub in, or you can, for a tech-free, which we'll assume this is tech-free, you do it this way, 0 to a, and then you get a cubed square root of that, and 2 on 3 equals 18. And then we will multiply it by 3 on both sides, and then divide by 2. Let's divide by 2 first. You get 9 times 3 equals square root of a. 27 squared is a cubed, and a is equal to 27 squared cube root. Pretty sure that just means you can cube root the function and then square it later. When you do that, you'll get square root of 27, which is going to be 3 squared, and you get a equals 9, which is a nice whole number, which sounds about right. And you can always verify your answer for these type of questions just by actually integrating from 0 to 9 for square root of x and see what you get. Moving to question B. The line x equals t and the curve 6 minus 2x. So first of all, let's just draw the curve, even though it's a linear function, of 6 minus 2x. So you get a very rough diagram here. X equals 6. It's going to be an intercept point, and then negative 2x. And just by subbing in y equals 0, you get x equals 3. It's going to be another intercept point on the x-axis. The line x equals t and the curve enclose an area of 4 square units. Find the exact value of t and explain why the other solution of your equation must be rejected. Let's go ahead and integrate this. 6x minus x squared is what you get when you integrate, just using the basic power rule. Sub in the points of t and 0. Slight miscalculation because it's the x-axis and the region. So it's actually going to be from, let's say, the t value here up till 3, because that's how it's actually getting enclosed. So we have this requirement where t must be less than 3, because otherwise, if the t value is like here somewhere, that's not going to actually enclose it with the x-axis. It's actually going to be integral from t up till 3. Sub in those points, we get 18 minus 9, whole thing minus 6t minus t squared. And this whole function should equal 4, because that's given to us in the question. That's what the value we're trying to look for. We got the brackets. All right, that makes it a bit easier. Move the 4 over to the other side, and you get t squared minus 6t plus 5, and hopefully we can find a solution here. And yes, we can. We can use -5 and -1. And this should give valid solutions. And now we just use null factor law. T equals 5 and t equals 1. Now, out of these two solutions, we are expecting one to get rejected. And in this case, it would be t equals 5, because we know that t must be less than 3. And t equals 1 gives a valid solution, so the answer is t must equal 1. So yeah, that's going to be all for today.